Probably Sanju Samson, maybe even Mayank Agarwal, now that he's made the team. If you had to pick the Indian team to Australia, which has already been made and Surya is not part of it, would you have taken Surya along? If not for one of those names that I mentioned, then in addition to?
You're asking really hard questions, aren't you? Yeah, look, I probably need to have the team list in front of me, but from what I've seen of Sanju Samson, I see glimpses of brilliance, but I don't see consistency. What I see with
मैडम बच्चों को बुला रहे हो फाइनल के लिए कि नहीं?
फाइनल के एग्जाम के लिए बात चल रही है कि फाइनल ईयर को ईएसटी लिखने के लिए बुलाएंगे 10 दिन के लिए।
कुछ जैसे मैं पढ़ा रहा हूँ ईएसटी को, तो काफी बच्चे कह रहे हैं वी वांट टू कम।
हाँ नहीं, ईएसटी के लिए बुला रहे हैं बच्चों को फाइनल ईयर के, और वो भी ब्रांच वाइज बुलाने का प्रोग्राम है। तो सबसे पहले कंप्यूटर साइंस आएगा 24-25 नवंबर के आसपास। कह तो यही रहे हैं, अब फिर कुछ बहुत तंग आ गए, ये कैंपस पे आ जाएं वही ठीक है, बहुत तंग हो गए अब तो। मैं तो इनके मेलों के जवाब दे दे के परेशान हूँ।
वैसे तो सब कुछ आ रहा था रास्ते में, कई स्कूलों के बच्चे भी आ जा रहे हैं।
नहीं, स्कूल तो खुल गए हैं। अर्नव का, मेरे बेटे का स्कूल तो 1 महीने पहले खुल गया था। वो कहते हैं अंडरटेकिंग दे दो और भेज दो।
मेरे बेटे
मैंने तो भेजा नहीं ना, अंडरटेकिंग दी ना बच्चे को भेजा।
नहीं, वो तो ऑप्शनल है ना, अगर आप जाना चाहते हैं जाओ।
हाँ, बसें चलती हुई मैं देख रही हूँ, स्कूल की बसें चल पड़ी हैं। एडमिशन की 150 सीट खाली थी। आज काउंसलिंग हुई है उसके लिए, सुना है जूम पे हुई है, ऑन इन स्पॉट काउंसलिंग।
ऑल ब्रांचेस में 150?
ऑल ब्रांचेस, कहीं कहीं पे तो ज्यादा हैं पहले ही।
वो हो सकता है कि उन्होंने पहले ओवरलोड कर रखा हो, पहले
1.5 गुना एडमिशन करेंगे।
और बच्चे स्टफ तो बहुत बुरा आ रहा है।
स्टफ तो बुरा ही आएगा। अब नंबर बेशक कितने भी आए हुए हों, परंतु स्टफ कैन नॉट बी टू गुड, आ ही नहीं सकता। और जो अच्छे हैं अब वो आईआईटी चले जाएंगे अभी जब एडमिशन। हाँ हाँ, ऑफर आने लग गई ना कुछ। यहाँ से भी तो अपने कैंपस के एक आध बच्चे को आईआईटी रोपड़ मिला है, किसी को ऐसे 1-2 खबरें आ रही हैं। तो एडमिशन तो शुरू हो गए वो लोग, परंतु अपना सेशन उन्होंने डेफर कर दिया है शायद 1 दिसंबर के लिए। अच्छा, मेरी तो क्लास है।
ये मैं पूछ रहा था, ये जो आप डॉक्टर कॉलोनी में रहते हो, ये कॉर्पोरेशन के अंदर आ गए? सराबा नगर आ गए? सराबा
नगर का तो मुझे पता नहीं, परंतु नहीं, डॉक्टर कॉलोनी तो नहीं आया अभी सर।
मैं घर लेके आया था सराबा नगर।
कभी कोई अब हाल में कुछ आया है?
मैं 6-8 महीने कोशिश कर रहा हूँ।
Good afternoon, friends. I'm sure you got my message that because I have a meeting tomorrow morning at 10:30, so I would have missed my class. So I have swapped this class with Dr. Mayank Rai. Okay, though there had been few other things which came up in between and interruptions, so I couldn't start in time. Thank you for waiting. And I think we will do some bit of finite state machine which we were doing. Okay. So we had talked about two kind of finite state machines. We said one is Moore machine and second is Mealy machine. And we had said that the next state is always the function of external inputs as well as the present state, but it depends upon external outputs, whether they are function of only present state or function of present state plus external inputs. So this becomes a Mealy machine and this becomes a Moore machine. So we will take some examples and we will try to do the machines. Now, for example, we had talked about counters. Let's say I have a counter which counts the sequence back to 0 and so on. So we said, what is the state machine? It is in state 0. State is itself an output. On next clock, it goes to next state, which is always 1. Then it goes to the next state, which is always 3. From 3, it goes to next state 6. From 6, it goes back to 0 and continues. Please, door be closed. Let me finish. So now there is a fixed sequence. So whenever in state 0, the current state decides what is going to be the next state and what is going to be the output. Here the output is 0, here output is 1, here output is 3, here output is 6. The binary code corresponding to the value. Okay. Now think, let's see another counter, which is, let's say, up/down bar counter. And let's say it is only a 2-bit counter. So it counts from, so depending on this external input, okay, let's say it begins at state 0. Now it depends on what is this control value equal to. Let's say I'm writing a short name for this control, u/d bar. So I have two options. If u/d bar is equal to 1, then I'm counting up. So my next state is 1 and my output is also 1 because the state itself is my output. Okay. If again here, but if it is 0, u/d bar is equal to 0, then my count should be 3. Okay, down counter. From similarly here, the possible states are 4. So if it is up, you go this way. If 0, you come down this way. Okay, if it is 0, you are moving this way. If it is 1, you are moving this way. But even this is a Moore machine. Why? See, the next state is function of external input and present state. Here, next state was function of present state, which was same as the output, or there is no external input. So next state is just function of present state. Here, next state is function of present input, present state. and is also function of external input here, because there is a one external input which is available as u/d bar. So it knows whether to count up or down. Accordingly, it will move to one of the two states. But when you see the output, here output is 0, output 1, output 2, and output 3. So output is same as state, which means the state decides what is going to be the output. So your external output is same as a state, or you can say is the function of present state. There is no role of any external input in the output. So it is a Moore machine. Now what we will do is, if this is clear, we will move and take another example. And for that example, we will do both Moore and Mealy machine, and then you can see the difference. The problem is, let's say, this is the FSM which we wish to design. This receives a bit stream X. So bits are coming, okay, like 0, 1, 0, so on, 1, 1, any stream. What this machine has to do, it has to pick a packet of 3 bits. That means it should look into the 3 bits and raise a flag regarding parity. So if parity is even, the output will be 0 and F will go to 1 if parity of those 3 bits is odd. You people try and write the any machine, whatever you can, and I give you 2-3 minutes and then I'll draw. Take out your paper and pen and do it. And if you are ready, you can let me know. I'll share the screen with you so that you can show me. Yeah, anybody who has done, raise your hand. Anybody who is listening? Anybody who is listening to me? Tarun? Digvijay Singh Parmar? Digvijay Singh Parmar? Tarun Kansal? Is anybody there in the class? Unfair. Am I not talking to walls? It appears I am talking to walls. Vansh? Abhinav Singh? Devang Mishra?
मैम
हाँ, या शाइना, क्या नाम है आपका बच्चे?
मैम आलोक।
आलोक, बट मेरे को तो आलोक नहीं दिख रहा है यहाँ पे। हाँ, आलोक ओरी, बोलो।
मैम मेरे को एक क्वेश्चन आप एक बार दोबारा समझा दो कि हमारे इनपुट हमारे को ये 3 बिट आएगा, तो हमें ऐसा सर्किट बनाना है कि अगर वो ऑड है
सर्किट
तो
नहीं बनाना, हमें अभी सर्किट नहीं बनाना,
जो भी मैम फिक्स वो
हमें FSM का वेन डायग्राम बनाना है खाली, कि
ठीक है।
हमारे पास एक इनपुट है, 1 bit at a time we are getting when we in serially, and when
मैम
we
1 बिट या
have
3 बिट?
1 bit at a time. So every clock I am getting 1 bit. When I have received 3 bits, I have to take a decision whether my parity is even or odd, and accordingly I output F, which says equal to 0 if it is even, and parity if it is odd, I will say it's 1.
यस मैम।
ठीक है, लेट मी डू, बट मुझे मजा नहीं आता जब तक आप लोग बोलते नहीं हो, इंटरेक्ट नहीं करते हो. सो एनी इफ यू फील एंड गुड अबाउट इट एंड वांट टू लर्न बेटर, प्लीज इंटरेक्ट. And FSM is something which you will kind of do much better if you interact and try yourself. Okay, so please understand the problem. We are getting serial 1 bit at a time. So it is a serial bit stream. Output is only 1 bit flag F. So my input is here, input is X, and my output is F. Okay, number of states I don't know because I have not designed my circuit. Okay, so let's design the circuit and then we will know how many states are required in the design. Let's say this is when power on turns on. This is my state, and any state name has to be alphanumeric, and along with that it should start from alphabet. So you can have any name, like any alphanumeric name, but must start from alphabet. You can even have S1, S2, S3, S4, so on like this. But I will use my own nomenclature, which tells me some information about my state. So I am here and I have one input X. So when the clock comes, I will get bit either as 1 or 0. So I'll start building up my partial parity. Now there are two conditions. Either I can get 1 or I can get 0. So this circle denotes, yes, please. Yes, please. Who has a question? None. And so this circle denotes a state, okay, and arrow denotes the transition from one state to another state, and it could be based on your inputs. Okay, so now I am in this state and I have input X. So I have two options. Either my X can be 0 or my X can be 1. Based on that, my here partial parity is even. Here my partial parity is odd. So they are different states. I have read first bit. Here partial parity is even. Here partial parity is odd. So I am using the state names to be even and O1. So even tells me why I am using this kind of a name is, it tells me straight away, yeah, my partial parity is even and I have read 1 bit. Okay, if you don't want to relate it, you can use S1, S2, S3, S4, anything, A, B, C, D, E, F, G, or whatever names you like. This is what I prefer to do, and it makes me do things easier. Now, if I am in this state, again, now my in next clock cycle, I again will get the second bit. Now, second bit can also be either 0 or it can be 1. Okay, if it is 0, my parity remains even but I have now read 2 bits. So I am in a different state. I have now read 2 bits. Similarly, from here, I can get either I will have 0. If it is 0, my parity remains odd. And I have read 2 bits. So I call it O2. But if I get 1, so 1 and 1 is even. And I have read 2 bits. So it is the same state. So if I get a 1, my parity is even and I have read 2 bits. So it is same as this state. Same here. This was even parity and I got a 1. So parity becomes odd, but I have read 2 bits. So this is the same state as O2. Okay. So now again, I have 2 options. And now this is my 3rd bit, which I am reading. So again, I can get either a 1, which takes me to O3. If I still get a 0, my parity is even and I have read 3 bits. Okay. Here also, if I get a 0, my parity is odd and I have read 3 bits. But now if I get a 1, my parity becomes 1 and now I have read 3 bits. Now I have read all the 3 bits. I should give a output. So on this state, my output F. See, we are drawing a Moore machine. So in Moore machine, your output is function of the state. So here F is equal to 0. In this state also F is equal to 0. Because I have not read all the 3 bits. And that is why F is 0 in all these states. But here, whenever my parity is odd, this is the state when I have read 3 bits and my parity is odd. So I am giving a result F is equal to 1. Though here also I have read 3 bits, but since my parity is even, my output will be 0. Now, if this machine has to go on, now this has read 1 block of 3 bits, but this should continue. The question had been every packet of 3 bits, it should give a result, whether this packet had a even parity, this packet had odd parity, and so on. So from here, now I will read the first bit again. So now when I read the first bit, again, it can be either 0 or 1. So if I'm here and I get a 1, so my partial parity is 1, so I go over here. If it is 0, I go here. Similarly, from this state, if I have 0, I'll go here because my partial parity is even. And if I have 1, I will go here because my partial parity is odd. Okay, this is Moore machine. Now you can see all the transitions are based on input. That means next state is controlled by external input and where I am, the current state. Whereas my output is the function of present state. If I'm in this state, my output is 0. If I'm in this state, my output is 1. Okay, so this is Moore machine. Now, if I do the same example using a Mealy machine, you will see the difference. Let's draw the Mealy machine. Again, this is the power on state when I start out, and I will read the first bit. When I read the first bit, so if my first bit is, I'll do the similar direction. I took 1, so I'm taking 1 here. Now here, because my output is function of external input also. So right here, I'll say my output is 0. And next state is my O1. Now this state is the same. I have read bit 1 and that has a odd parity. If it is 0, I'll still output 0 and I'll say my partial parity is even and I have read 1 bit. Similarly, from here, when I read the second bit, if it is 0, since I have not completed reading all the 3 bits, my output will remain 0. Parity is still odd and I have read 2 bits. But if I get a 1, my parity becomes even and I have read 2 bits. If I get a 0, I have this. If I get a 1, now is the difference. Now I am reading the third bit where I now know the result. So if I am in this state, okay, and I get a 0, okay, if I get a 0, my final parity is odd. Okay, so I can go over here and I will say if I get a 0, my output is 1. I don't another state. I can output my here and I can, because I have completed reading the 3 bits and now I have to restart reading the next packet. So I can go to this state. If I have input as 1, my parity will become even because this was odd parity. So now it becomes even. So my output will be 0. So both the transitions can come over here. Similarly, from here, since I was having even parity, so if I get a 0, my parity remains even. So my output is 0. But if I get a input 1, my output becomes 1 because parity becomes odd. And I can go back to the same state. Okay, my next state can be the same because output is function of external input and can be shown on the transition. Now I am again here, so I'll start reading my next packet of 3 bits and I will move. If it is 1, I'll go here, 0 here, next read the next bit, either here or here, I go back. So you'll see here I need 7 states. Here I need 5 states. Okay, so here, though, because there are 7 states, these are 5 states, it needs a 3-bit code, and 5 state also needs a 3-bit code. So maybe I don't see a reduced hardware, but it at least tells you that when you are trying to make a Mealy machine, typically you will have less number of states and you are likely to reduce the overall hardware, though it will still depend upon the number of states and how many bits are required to represent it. Okay, so if you draw bigger machines, maybe the reduction is large and you can find that the Mealy is more compact, but not always true. Here, there will be only minor gating differences, but when you reduce it to the hardware, you will have something similar or almost same hardware because number of flip-flop remains the 3. Okay, so now there are few things. Is that clear? How to draw a Moore machine, how to draw a Mealy machine? I think we will take few more examples. I can pick up one more example today and then I'll leave some examples with you to do. Okay. Now, and then we will talk about few more things. The few more things which I will like you to ponder upon and think is, what if you draw redundant states? Now, for example, here, we said from here also you are coming over here also you are coming over here. Maybe you didn't understand and you drew a new state over here. Instead of coming to E2, you had drawn a new state and you continued from this state as well, taking 2 transitions and you did it. Okay, so is that everything lost or everything gone or everything out of control, or you will not be able to design your circuit? No, it's not so. What you can do is, what can be done is, there is fortunately, if you have redundant states, there is a process of state reduction. Okay, so we will do, how do you do the state reduction? So if there is any redundant state in your state machine, that will get eliminated, and you can reduce your state machine to the compact state machine, the smallest possible state machine. Okay. Second issue is state code assignment. Now see here, you have here 7 states. You want to leave just one code. Which one code you should leave out? And these are 7 states. Who should get what code? Okay. Should I try to just number like 1, 2, 3, 4, 5, 6, 7, or there is some other strategy to do it? There are various ways of doing it which optimize your hardware. So we will, if time permits, I'll take you through one method of state assignment. How do you do so that you get a optimal circuit? Okay. For example, here you are only choosing 5 codes out of 8. So which 5 codes should you choose and how you should assign those codes? That is the problem. Okay. So these are 2 things we will like to talk about a bit later. But let's say for today, we will take one more example and then we will close. Now I am taking an example of sequence detection. This is something which we keep on doing. We took counters, we did using shift registers. Now we are making finite state machine we are using for sequence detection. Everything is a sequential circuit. The only difference is how you connect those flip-flops. That is the whole story. Okay. Now here we are first talking about only the Venn diagram. So let's say again, I am taking a very simple example. Let's say my example which I take is this. There is again, which means that this is the sequence detector. On input side, I am getting a bit input. Serial bits are coming one by one. And output is, it is giving again for every input, there is a output. And whenever there is an occurrence of this sequence, the output becomes 1. So whenever there is last 4 bits had the sequence, your output becomes 1. So, or let's say sequence is going this way. So I will start getting from here. So I'll detect this. As soon as I get this, I'll raise a flag over here. So for example, if you are getting a sequence like so on, this is a bit stream which is coming. So this is entering first, then this. So every time I have this occurrence, my flag should go high. So this is this. So 0, 0, 0, 1. Now here, this is 1, 0, 1, 1. No, I am not interested. This is also not there. Here, yes. So again, this is 1, 1, 0, 1. So here flag should be 1. So now this flag goes on just after 2 bit. So this bit was there in this packet as well as in this sequence. Here, no. So 0, 0, 0, 0, again it should go 1, 1, 1, 0, 1, so on. So every time it has to track occurrence of 1, 1, 0, 1. That is what it is tracking. Let's draw a machine. You can draw a Moore machine. You can draw a Mealy machine. I am now drawing a Mealy machine. Okay. So let's see when my power turns on. This is my start state. This time I'm labeling it as ST. Okay. I get the first bit. Now, if my first bit itself is 0, that means I have not got any valid bit in the sequence. So I remain in the same state. If I get 1, my output will be 0, but I know I have got first valid bit. I'm calling it state 1. I have one valid bit. Now here again, either I can have 1 or I can have 0. If I get 1, my output will be 0 because full sequence has not been detected, but it is a valid digit. So I say I have received 2 valid bits. But if I get a 0, all gone waste, I will go back over here and I will relook for 1. Okay. Now here, now I am looking for 0. If I get a 0, then yes, this is my valid bit, but it is only the third valid bit. Okay, so I go to S3. But if I get a 1, then what happens? Now, because I already had a 1, so, and instead of 0, I got a 1. Maybe I will get a 0 next time. So I'll remain in that next state because my previous 2 bits are still 1. Okay. Now in S3, now I am looking for my final bit 1. If I get 1, I have found the sequence. But this one could be start of my next sequence too. So if I get a 1, I'll come over here. So this is 1 with output as 1. I have found the sequence. But if I get a 0, all gone waste because 0, 0. Neither it could be a start of the new sequence, neither it is valid. So I'll come back to my this state 0 with output at 0. Okay, and my FSM is done. How do you check whether you have completed the FSM or not? Is there anything pending or not? Every state you see how many combinations are possible. If you have just one bit variable, you have 2 options. So there should be 2 arrows going out. Now see, this is 1 arrow and this is 2nd arrow. Okay. Similarly from here, 1 arrow, 2 arrow. From here, 1 arrow, 2 arrow. From here, 1 arrow, 2 arrow. So my state machine is complete. Okay, any number of input coming arrows can be there. But if I had, let's say, 2 variables on my input, okay, maybe there was some other variable A. So now A and B are binary inputs. So I'll count what are all possible combinations. So I can have 4 combinations. Okay. Now, if I have 4 combinations, so I should have 4 arrows going out from each state. So it just depends upon your inputs, how many options you have, and accordingly, you can draw the state machine. Is it clear to everyone? Any doubt in this? So now I'll leave you with one example. Yes, please.
मैम जो पहले पिछली स्लाइड थी उसमें जो मूर मशीन है उसमें पूछना था.
हाँ, ये वाली में बोलो.
लेफ्ट हैंड साइड वाली में.
हाँ, लेफ्ट हैंड साइड इज मूर मशीन. हाँ, बोलो.
इसमें जो मैम ऑड 3 में अगर मतलब 1 आएगा तो ये मैम ऑड 1 में मतलब एक 1 तो पहली है, तो ये इवन नहीं हो जाएगा फिर?
नहीं, एक 1 पहले नहीं है ना, अब ये पैकेट तो खत्म हो गया 3 बिट का, अब नया पैकेट पढ़ना शुरू किया ना इसने। यहाँ पे ये जो बिट्स थी, bit 2, bit 1, bit 0. So this packet was one packet, this was second packet. So जब ये पैकेट खत्म हो गया, इसकी कहानी खत्म हो गई। अब इन 3 बिट का की पैरिटी बतानी है उसको, तो
मतलब
यहाँ पे पैरिटी ऑड थी या इवन थी, दैट इज नॉट एन इशू. This circuit is telling the parity of 3-bit packets. Okay. So ये जो 1 था, ये फर्स्ट बिट थी इस पैकेट की. अब यहाँ पर जब यहाँ पे ये 1 आया तो ये वाला पैकेट शुरू हो गया है, ये वाली बिट है. ठीक है.
ठीक है. यस मैम.
तो प्रीवियस बिट का इससे कोई लेना देना नहीं है.
ठीक है.
और बोलो. Okay, if you people have understood, okay, just solve one more problem. I am giving you one more sequence detection, and send me, take a snapshot and email me. Again, you will write your subject as UEC 612. This should be the subject, and you should send me the mail at alpana@thapar.edu as before. Now the question is, again I am giving you not a very different problem, but I am adding something. Again it is a sequence detection, but now you will detect the occurrence of 2 kind of sequences. Either you are getting this or this. Whether you get this or you get this, your output should, whenever either this happens or this happens, your output flag should go 1. So again, on input, you still have a 1-bit stream coming. These are bits which are coming like this bit stream. So either this occurs or this occurs. You are checking now 2 sequences simultaneously. If this happens or this happens, raise your flag for one cycle on the last bit. Okay, so kindly try this and send me the solution, what you did for it. Okay, so we will stop over here for today. If there are any questions, I can take them up even now, or if you want to ask me in the next class, we can take them up in the next class. The only information for you is tomorrow I will not be taking class at 10:30, and we will meet on Monday. Is that okay with everyone? Any representative? कोई भी नहीं बोलता. कहाँ है रिप्रेजेंटेटिव? ठीक है. Okay, so let me close the class if there are no more questions. And I expect more of you to respond to my queries because I am noting them as sessionals. Okay, so those who submit to me will definitely have something in return. Okay, then have a good day. Bye.